All right, well, thank you, Willie. Thank you, everyone. Coming in, grab a seat. There's more chairs here, some over that way. Righto. Well, I hope you're enjoying the evening so far. Good music. We'll do a little science chat here. Get to go look through the telescopes later. Who's looked through these telescopes before? All right, awesome. Who's looked through this before? Yeah, that's a little harder to get to. That's right. You can download this, play with it, try to recreate it. Yeah, that's right. It's actually not too bad. But yeah, you want a good size hard drive. Exactly. So I'm going to tell you some of about some of the things I think are really interesting that we've learned over the last year, thanks to the James Webb Space Telescope, which will be our hero for the evening. There's a mock-up of it right there, which of course is responsible for this beautiful image here in the background. I'll be showing a lot of images from NASA, ESA, Canadian Space Agency, a lot of PR press images, talking through some. Just want to say, if anyone has questions, you can feel free to raise your hand, pipe up here, and I think we'll have some time afterwards for a little question and answer as well. And yeah. So one other thing, just to set the stage, this beast here is kind of the latest in a line of very powerful telescopes, which I think you could directly trace back to the one right behind me, the Great Refractor, the 36-inch here, which back in 1888 was the biggest, most powerful thing we had. And it's gone up and up and up in aperture, telescope size, sensitivity through the ages, and now we have this gold-plated 6.5-meter thing in space. And yeah, I'll start by telling you a little bit about its journey out there, and then a little bit about what we're finding and how we get these images. So, ready? All right, onward. The mirrors worked. All of them. All of it, right? More than one. It's amazing. It's actually pretty incredible, isn't it? So to set the stage, you've probably, until about a year and change ago, pretty much all the really spectacular images, not all of them, but many of them that you've seen of space, anything in the sky, would have come from this guy on the right, the Hubble Space Telescope. And lately, we've been seeing a lot from the James Webb Space Telescope, which in many ways is the successor to Hubble, the next generation telescope, decades in the making, more powerful, key differences as well. So just to show to scale, okay, these are to scale, also the primary mirrors, these are the light gathering elements with a normal size human there for scale as well. So there's the Hubble mirror, here's the James Webb Space Telescope mirror. By the way, I'll refer to it as Webb or JWST or maybe James Webb or whatever, different names. But what do you notice? A couple key differences. Yeah, size, this one's bigger.
Hexagon mirrors?
Hexagonal mirrors, plural. Yeah. So this is a segmented mirror telescope. It's not just one big mirror like the Hubble, which is 2.4 meters, but a whole series that lock together. Yep. What else is different? Yeah?
Are the panels flat on the James Webb, or are they also...
They're curved, yep, in a very, very precise manner. They're very smooth, but yeah, they have the right curvature to reflect light to a common collecting point, focal point. Yep.
Is there a reason for the difference in color?
Yes, the difference in color, exactly. There is a reason. There's absolutely a reason. James Webb is plated with gold because we want to bling it out. No, that's, well, Yes. So the Hubble Space Telescope mainly works at visible light, and aluminum reflects very nicely at visible light, ultraviolet light, near-infrared light. James Webb Space Telescope looks at different wavelengths or frequencies of light, longer wavelengths, and gold turns out to be a really good reflector in that regime. Now it's yellow colored, that tells you that actually like blue light is not being reflected back, but this telescope doesn't look at blue light, so that's all good. But it really is gold plated, just a little bit. Yeah, so that color difference is key. So there we are again, to scale these two observatories, both of which are floating around in space, taking data as we speak, pretty much 24/7. And just a little bit about that color difference and why Hubble's mirror is silver, illuminized, really. And the James Webb mirror is yellowish, gold-plated. All right. So who loves going to the zoo? I like going to the zoo. I like taking my kids there. We have a lot of fun. We love the meerkats. We don't have crocodiles at the Sacramento Zoo, but we've got the freshwater American alligators. Pretty great. And here is what they look like, right? You go to the zoo and that's what you see. Now, that's invisible light. That's the light that our eyes are sensitive to. That's the light predominantly that the Hubble Space Telescope records, although it's got a range of instruments operating across a range of the electromagnetic spectrum. Now, I mentioned the James Webb Space Telescope doesn't really look at optical light. It gets down into red light a little bit, but not so much. It's really longer wavelengths, the infrared, where it really does great. And things look a little different there, and that's kind of part of the point. So if you go to the zoo with your night vision goggles or your infrared camera, the animals look like that.
Cool.
Yeah. So what's different? What are we seeing?
The light is passing through their bodies because it's a longer wavelength.
It's not going to go right through their bodies, but it's going to radiate out of them. So actually, this is an interesting thing is when we look at this, we're just really seeing sunlight reflecting off these creatures. Here we're seeing their glow, the light that actually radiates from them. Yeah, and the key difference between a meerkat and a crocodile in this case is what, biologically? Yeah, a cold-blooded animal and a warm-blooded animal. Yeah, and those warmer animals shine brighter in the infrared. And in fact, the scale over here even tells you a rough temperature that goes with that. So we're about like that too. We'd be like a meerkat. Yeah, nice and bright out in the infrared. So the key thing is when we look out in space with JWST, we can look at the same space, same sky, different light, different wavelengths. So it's not just a bigger, more powerful telescope. It lets us see things literally in a new light, a different light. And that's where a lot of the discovery comes in. That's what's really fascinating. So one thing to really emphasize, this telescope, it's a $10 billion machine. It is incredible. I mean, and it shows. It's really a testament to the ingenuity of mankind that we're able to build this kind of thing, launch it off into space, and it works. Critically, it works. It really does. It wasn't guaranteed, as far as I know. But anyway, so here it is. Did anybody get to see it? I didn't either. I know lots of folks who did, though. But yeah, it's big. You can see, here's a person up here for scale. So this is in the clean room in Northrop Grumman. So we'll just look at a few images of this. Of course, we don't get to go take pictures of it up close anymore. It's, pretty far away these days. We'll see that later. But there it is. It's a lot of work, decades really, to get this thing into shape. A lot of very careful testing, inspection, the whole works. Remember it's segmented, these different parts. So here's a person just inspecting, looking at these different segments. Again, little tiny thing, gold plating. You got all these electronics in the back. These mirrors all have to be fit together, aligned just beautifully, perfectly to within a very small tolerance in order for it to work properly. So really an incredible machine. And it's been a labor of many, many people over a very long time. I guarantee you this is only a very small subset of the people who made this observatory happen. So if you see any of them or any others, give them a high five, buy them a beer, say thank you. It's been a massive team effort. There again, that's a model for scale outside the Goddard Flight Center in Maryland, where a lot of folks do this, and just not too far from the Space Telescope Institute where they run the operations. Yeah.
That's an actual size model.
I believe that is a full-size model. Yep, scale model. Yeah, and just yeah, to kind of envision it. So that main mirror, diameter across there, that's about 6.5 meters. Give or take, order of magnitude, size of this room. And this is the sun shield deployed down there, and I think the usual metric is it's about the size of a tennis court. Yeah, so.
Those had to be unfolded.
Yeah, that's right. Yeah, real tricky. A lot of literally moving parts. Yeah, so we'll see that, because I think that's kind of a fun, interesting part of how do you get it in that configuration up in space. That's tricky. You can't just launch it like that. It wouldn't work so well. Yeah. So yeah, here it is again. So that was the model before. Here's the telescope itself. Again, in the clean room, Northrop Grumman. Here it has the sun shield out deployed, but that all gets folded up, packaged into something a lot smaller. You can see in this case the wings of the telescope. You've got several of the segments here, and the remaining 3 on each side are kind of tucked behind it. It's all snapped into form. Basically, you need to make it small enough to fit into a rocket to launch. So we'll see that in a bit. Anyway, so yeah, a little bit about Webb's journey. Did anybody kind of follow it before it launched? Yeah, I did, especially because I was like, okay, am I gonna get to use these data? Is it going to make it? Is it gonna get down to South America and launch up and take data and all that? And so, it was a process, especially when you're really anticipating it. And, I didn't even build the thing. I can only imagine. Huh?
How many years from design to...
Oh my gosh, decades.
Was it better than a decade?
Yeah, I mean, it's been, longer than I've been an astronomer, really. I remember more than 10 years ago, Congress was, deciding to shut it down and then bring it back. So it'd already been going a long time since then. Glad they did bring it back, incidentally. Yeah. So, yeah, it's been quite a journey. Here we're just going to walk through the last stages of the little journey. Kind of the terrestrial and then extraterrestrial part. So, nice thing, it was, largely built and assembled here in California, Southern California. Down Northrop Grumman in particular. And it had to get put on a boat to go shipped to the launch site. So here's the boat, the Colibri, the old hummingbird. And so it had to sail down from California, down south through the Panama Canal, dodge pirates. Not really, but there was a little bit of a joke about pirates for a while that I understand some people didn't appreciate so much, but it was just a joke. Over to French Guiana, which is the launch site. So basically a tropical island off the coast of South America, where, equatorial, pretty close. So you get a nice launch pad out to space, and you've got a big old Ariane rocket up there. So a little bit of a closer look. Let's come in here. Okay. And this is a big telescope, okay, size of a tennis court, mirror the size of this room. And it has to fit in there. And specifically, it has to fit up there in that nose cone in order to launch, right? To get out to space. So this is, one of the many really incredible aspects of this observatory and engineering marvels, really. But there it is. So just imagine that whole telescope is folded up, packed really nicely, really tightly up in that nose cone, which is probably going to shake a lot, right, on the way up. And there's a lot of little moving pieces in that telescope too. So, that part I imagine could be a little nervous. And anybody watch the launch? Yeah? All right. Awesome. I did not watch it live. Okay, it was Christmas morning at, about 4 a.m., something like that, West Coast, California time. And, I've got a couple little kiddos at home, and Christmas is a fun day, and I was like, yeah, I'm not going to get up at 4, be super tired. But my 3-year-old at the time and I watched the video of the launch, a couple hours after it happened, and that was lots of fun. So another fun aspect, the launch date had been, postponed many times. There's a comic about it. And I think it was September-ish, 2021. There was a date set for then, and then it got pushed back to later in the year. And a colleague of mine was joking, oh, it's got to be a Christmas present, Christmas launch. that it actually was. So we all got this wonderful Christmas present. The real present was launch went well and it worked, right? Yeah, would have been a little bit of a downer otherwise. But hey, we got the good stuff. So there it is, blasting off Christmas morning, 25th of December, 2021. Pretty recent, you know, so appreciate that this is pretty brand new. And off it goes. So nice mock-up again, this whole thing, and that's about how it looked folded up. Whole observatory had to fit in that nose cone, and then had to turn into the full deployed version of itself. And that's a process. And meanwhile, it's traveling way out into space, okay? So there's this whole unfolding sequence. First, okay, if you watch the launch, right? Gosh, the launch video, I'm sure it's still up and you can check it out, and it's a few hours long, something like that. So the first part, obviously, liftoff is really cool, and then it kind of, you know, rattles around a bit, and then separation is really cool. So about a half hour in, you get some exciting parts. This actually pops off, floats into space autonomously on its own. The solar panels come out, so that's this next step here. Got to have power to the observatory. So that's a big part. When the solar panels come out, the power turns on, you're like, yes, we have electricity. Otherwise, we'd have a big chunk of space junk. But it works, it has power. Eventually, you know, later, a few days later, sun shield deploys, the mirror snaps in place, and meanwhile, it's traveling way, way, way out, million or so, 1.5 million kilometers off from Earth. And we've got a little, so this is about a, you know, couple of weeks to fully deploy, month to get out to orbit. We're not going to watch the whole version of that because it's not that long of a talk, and that would be kind of boring anyway. So instead, we're going to see the short version, okay, and just a little schematic of where this orbit is, way out past the moon, right? So it takes a little while, about a month to get there. And here's how it works, okay? So the first parts happen kind of quickly, but really that's 3 days to get the shields deployed. And this will loop through so you can see it again, where you go from that compact version in the rocket, solar shield coming out, so those whole things have to deploy, the 5 layers separate, and then finally those mirrors, the side mirrors, snap out. And the secondary mirror reflector there snaps into place. So there we go. That's what had to happen. One of the many things that had to happen, and every little part of that had to go right, and it did. And one of the best parts actually was I don't know, a lot of great parts. The orbital trajectory, right? It takes a few burns of rocket fuel to get out there, and that all went really well. So that means there's still lots of rocket fuel, lots of propulsion on board the spacecraft to keep it in place so it can keep operating for a good long while. Yeah.
What's the purpose of the sun shield? Guard it against the sun rays or to catch it?
Against the sun rays, yeah. So you've got the solar panels for energy, for electricity, but the telescope, the whole thing has to be very cold. So operating in the infrared, right? We glow really bright in the infrared. Telescope, the 36-inch back there glows really bright in the infrared. You don't want your optics all like glowing when you're trying to, you know, look at faint stuff. So you have to cool it down to reduce the thermal radiation. And so that sun shield is very important for keeping sunlight off of it. Otherwise it would heat up just from absorption of the light.
I would assume the temperature appears to be low.
Yeah, exactly. So the temperature, if you're not in the sun, if you're in the shade, it's nice and cool. So that's exactly the point. You want to be in the shade. And those 5 layers keep it nice and shaded, nice and thermally balanced. You'd be on the far side of the moon, be nice and cold there too. Near side of the moon, not so much. Well, okay, sorry, sunny side of the moon. That one varies. So if you're on the sunny side, it's warm, and the dark side, it's cold. Yeah. So this observatory is in a pretty special place, not just way past the moon, but it's orbiting around the Earth-Sun system in what's called a Lagrange point, this L2. Anyone know what that is? Know what its significance?
0 point of gravity pulling one way and gravity pulling the other.
Yeah, so Hubble, the Hubble Space Telescope, which is over here, okay, and this part is not to scale. It orbits around the Earth. Every 90 minutes or so it goes around the Earth. And the moon orbits around the Earth about once a month, 28 days or so. At L2, objects at that position, where the sun is in the opposite direction, they actually orbit around the sun, not around the Earth. And the sun's gravity and the Earth's gravity combine just the right way to keep it moving directly in line. Earth, sun, observatory. Like so. Now, the telescope isn't exactly at L2, which is really just a point there, which is unstable. But it's in this, what's called a halo orbit around L2, that keeps it basically from catching Earth and Moon shadow. Yeah?
Where is L2 with respect to Earth and Mars?
So Mars is way further out. Yeah. So, yeah, basically you've got Sun, Earth, Moon, L2, and then Mars is quite a bit further away. Also orbiting the sun just a lot slower. So the cool thing about L2 is it orbits the sun at exactly the same period as the Earth does. Yeah. Yes?
What is the radius of the orbit around L2?
Let's see. So, whoops. Okay, if I go back there. So it's about 1.5 million kilometers or 1 million miles further than the Earth.
Right, but
Yeah.
I assume it's orbiting L2. It's not stationary at L2.
Oh, yeah, got it. Right. So you're asking, like, what's the radius of this orbit? I'm not sure exactly what it is, but it's enough that basically if you draw a line from the sun through the moon, that the shadow that the moon makes at any point of its orbit, that area is going to be smaller than the orbit of the observatory around L2. So it's intentionally staying out of the shadow of Earth and Moon. Yeah. Anyway, this is a cool video that the folks at NASA Goddard put together that helps visualize exactly how it's orbiting. So, it is in that orbit around the L2 point, but in such a way, right, and the magic of that L2, the science of that L2 is that it's just right in line. So it's always basically directly opposite from the sun.
On a different plane, right, than the sun and the moon and Mars?
Yeah, that's right. That's right. And I think the plane that it shows here isn't exactly the orbit that it's on, but yeah, it's not in line with that. Yeah.
Why is it wobbling out?
Whoops, sorry. The kind of, which wobbling? Like the, yeah. Yeah, so it's on a trajectory on an orbit that basically follows this path, kind of orbits around this unstable L2 point, and it gets a little burn about every 2 weeks, I want to say, a little bit of a thrust from the propulsion on board to keep it roughly in that orbit.
That'd be sinusoidal tracking, isn't it? Since it's rotating, and it's forward, it produces a sinusoidal curve.
It's about like a sinusoidal, yeah. I don't think it's exactly sinusoidal. Yeah, again, I don't remember exactly what kind of orbit it's on. It had a whole range of different possibilities depending on the launch window, and I think the one it's in is called the halo orbit, as opposed to, I think this one might be showing what's called a Lissajous orbit, but I'm not really sure. It's not quite my specialty. But anyway, that's about where it is. Zooming around out there. And again, working, hooray. So, and here is, this was kind of the first, at least to me, indication that it was actually working. This was the sharpness check. So the observatory has several scientific instruments on board, and they're shown here. Slightly different wavelengths, different fields, they do different things. But the first check is, okay, you've got your telescope out there, setting everything up, point at the sky. Is it aligned? Is it taking good, sharp, high quality images? And you look at this and the answer is yes, absolutely. It is. It's great. And you can see it's nice and sharp. Anyone remember when Hubble launched and the first images came back? Yeah, those optics weren't so great, it turned out. There were some problems. Luckily, Hubble could be repaired. This one, not so much. So it had to work. And it did. And the way you can really tell is these, when you see the spikes, those like 6-pointed spikes off of the stars, you're only going to get that if the optics are really aligned just right, everything working well. Yeah, so that's the diffraction pattern coming from the telescope itself. So, hooray. Everything came out. And then, you know, this came out earlier, I think, than the first science images. But, oh man, when the science images came out, right? Not often that astronomy stuff gets on the cover of Time magazine, or, you know, gets unveiled by the President of the United States, which is what actually happened with this one, right? So, pretty amazing, and it really does look spectacular. So I hope this just gives you a little bit of the appreciation of what went in to making this image happen, to making this telescope, this observatory work. Really just scratching the surface again. It's been decades in the making. Yeah.
If it's taking images on the infrared, is that like colorized or documented or something like that for the picture? I'm sure it's like what you think it is, but is it like an actual image or is it a representation?
Yeah, great point, because yeah, again, it's yeah, good to keep in mind. The light, this is an actual image. It's just made of light that our eyes can't see. Wavelengths that are too long for us to perceive. But what, you know, if you take an image with your camera, your phone camera, you basically get a red, green, and blue and put them together and make a color image. It's really red is longer wavelengths, blue is shorter wavelengths, green is somewhere in the middle. And when you see these images, it's basically the same approach. It's three different pictures taken at three different wavelengths of light. And the shorter is blue and the longer is red. And so it's a false color in the sense it's not what our eyes would see. Our eyes don't see this at all. But it is colored in that sense. The blue and red mean the same physical thing as they do to our eyes. But yeah, if we were to look at this in optical light, we'd see different colors. Quite curious. But that's part of the beauty of it, really. Yeah?
If we were like closer to where these things are taken, out of curiosity, like, would we see it in visible light?
Oh, you can see most of these galaxies in visible light. Yeah. Yeah, exactly. We're just looking at the infrared light instead. Yeah, which can be very powerful. We'll see some examples why. Here's just a nice little comparison. So this is, I think it's a mix of visible and infrared, actually, although I don't remember. But this is an image taken with the Hubble Space Telescope up there. Okay, and what do you think? Yeah, it's actually a pretty awesome image. Pretty remarkable. I mean, these little dots are faint. You know, it's by no means the best image Hubble has taken, but it's a pretty good image. If you go look at this patch of sky with a 36-inch back here, you won't see much. So you can appreciate a little better, right? I mean, Hubble is nothing to slouch out. And that's what it looks like in the infrared with the James Webb Space Telescope. That's what a $10 billion observatory gets you. That is cool. I mean, look at the structure. This just blows my mind all the time. Yeah?
So what causes the spikes?
So the spikes are caused by diffraction. So it's the shape of the telescope itself, the mirrors and the support structure. And it's actually light acting as a wave and diffracting around the mirror and the optics in the telescope that gives it those spikes. And you only get that when your optics are basically perfectly aligned, what we call diffraction limited. Incidentally, that's something that you can achieve from the ground. It's very hard to do, but over here at the 3-meter telescope down the ridge and actually Ellie is one of the people who really, make that happen. This technique, from the ground is pioneered here. But yeah, those spikes, again, just tell you that you're getting really good image quality. Also the fact that it looks so nice and clear and crisp and you see all the detail. Very different from what Hubble looked like originally. But you see the same, in Hubble you get these same telltale spikes from the diffraction pattern. Yeah, this I think is about 5 hours. And I'm want to say for Hubble, I think it's of order about 3 hours, although I don't remember with that exact image. Not that different. So the quality difference is really the sensitivity, largely. Yeah.
What exactly are they looking for? Stars or?
Yeah, great question. So almost all the objects you see are galaxies, which have, millions, hundreds of millions of stars in them. Hundreds of billions of stars in them, depending on, which galaxy. Except the big bright things with the spikes coming off, those are stars which are within our own Milky Way galaxy. And the telltale sign, if it has the spikes, that's a star. It's basically a point light as far as you can tell. And if it doesn't have spikes, it's probably a galaxy. It's probably very far away. It probably has of order 1 billion stars in it or more. Yeah, these big yellow ones are really, really big galaxies. Yeah. Exactly, yeah. So you have these gravitational lensing effects. Yeah. And actually, I think if we go to our, let's see. Yeah, we'll go to the next one. But yeah, these things here, you get these weird distorted looking bits. Yeah, and those are galaxies whose images have been warped by foreground masses. That's a whole other interesting story. Yeah. So you get so the thing is actually everything has the spikes. It's kind of weird. It's a property of the optics of the telescope, but the spikes come off of basically a point. And for a star, all of its light is essentially at a point as far as the telescope can tell. It can't, resolve the surface of a star. But a galaxy is made of a whole bunch of stars. It's distributed on the sky. And so what you really have is little spikes coming from every point of the galaxy. Each one is relatively faint and they blend together and you don't really see the spikes. It comes out as a bit of diffuse background light, effectively. Yeah, but it's really only in the stars where you see the spikes. Yeah, so it's actually a great question. It is there. You just don't see it. For the best, really, otherwise there would be all sorts of stuff. Yeah, all right. So I was going to tell you a little bit about some of the actual scientific work that this observatory is doing that I'm particularly interested in. And part of that is searching for the earliest galaxies. The first galaxies that we can find, the most distant ones that we can find. And there's this little trick. When something's far away, okay, light doesn't travel at infinite speed. It takes time to get places. And so the farther away something is, the further light had to travel. And that means the further back in time we see it, which is pretty cool. So anyway, we can imagine, go back about 13.5 billion years, no stars have formed in the universe yet. It's just darkness, except for an infrared glow left over from the Big Bang. And then, at some point, the first stars turn on, start lighting up the universe, bathing it with light, optical light that our eyes can see. And they also make the first heavy elements. Basically everything other than hydrogen and helium is formed in stars. We'll get to that later. That's an aspect I'm fascinated by and work a lot on. And it's unclear exactly when this happened and how the physics works to actually make the first star before you have heavy elements. There's some really interesting questions there. So it's a bit of a quest to go back in time as far as we can and try to get to those first sources of light, that cosmic dawn. We're not there yet, but we're getting closer.
So you would think that 13.1 billion years ago you'd only have hydrogen, helium stars, but I heard somebody saying that there's heavy metal stars, which should not have formed for, well, that's no problem, right?
Yeah, we'll see this. Well, so the first stars very quickly make lots of other elements. Yeah, but let's just take a look back, see what there is. This is what I like to do. I'm an observer, so I kind of point things at space and see what there is there. This is an artist's depiction. Yeah, exactly. This is just art. Imagining what this may have looked like, kind of the first sources of light, ionizing the universe, glowing, lighting up the universe. This is what we actually see. Okay, same image again. And then I get really excited because, wow, this is a great image. So yeah, again, somebody pointed out, this is this yellowish looking stuff, these are very, very massive galaxies, moderately far away. They act as gravitational lenses, which actually magnify stuff behind them. That's, again, a whole other thing, but it's pretty cool. So, what do you think's the most interesting looking object in here? Ooh, yeah, there's some cool stuff up there. Some streaks. Oh, like these, we got streaks. We got, yeah, these are. Ooh, yeah. Yeah, I found some of those. And then if you're looking for really, really distant galaxies, far back in time. Oh, yeah, that's it. The red ones, yeah. So what do you think? What looks...
The oldest ones because red light travels the longest.
Oh, yeah, the light gets stretched out. Yeah, you're actually jumping ahead a little bit. Hold that thought. Yeah, so I'll tell you what galaxy that I think one of the most interesting ones in this whole image is here. You're probably not going to believe me. Okay, but let's see. From back here, does anybody see like a fuzzy, I'm going to laser point, fuzzy red dot there? Yeah, yeah. Isn't that cool? So cool. Okay, so the Webb Space Telescope doesn't just take images. It's very good at taking spectra, which is where you take the light and disperse it as a function of wavelength, and you get something that looks like this, a lot of wiggles, okay, but you're spreading out the light versus wavelength. So there's that object, kind of blown up a little bit, so you can see all its glorious structure, right? Isn't it pretty? Yeah, anyway. What's really cool is, yeah, so this galaxy, that's 13.1 billion years back in time is when we're seeing it, which is about 600 million years after the Big Bang. And we can tell very clearly, based on its spectral signatures, and exactly, okay, so there's hydrogen, lots of hydrogen, no surprise, universe is full of hydrogen. Yep, and there's neon, and there's oxygen. These elements had to have been made by stars, previous stars that already, not just formed, but formed, burned up, exploded, and then dumped a bunch of heavy elements into the surrounding space for the next stars to form out of. So already, just half a billion years, okay, that's pretty short in cosmic time. After the Big Bang, you already have this enrichment of the heavy elements. And we can see these things just so beautifully clearly with this observatory. Yeah. So basically add those up. About 13.7, give or take, is, our rough measurement. But yeah. And certainly any time we can see an object, we know that we're seeing it sometime after the Big Bang.
Wasn't there an article in the paper just the last few weeks that was sitting there saying that they're seeing size and accretions that supposedly couldn't have been formed that large that soon?
Yeah, there's a lot of those. I don't believe them yet. Yeah, so.
Is there an announcement by NASA that the Big Bang now is 26 billion?
That was a recent, also I wouldn't believe that one yet. That's one, that's one or two well, that wasn't from NASA, I don't believe. No, but I think, I heard about it, but I haven't kept up, so. The detector gap, yeah. So I'll draw you a picture later. There's two detectors that the light gets collected on, and it's basically one detector. They don't exactly butt up against each other. There's a little space. The light gets spread out, and there's a little strip where you just don't catch anything. Yeah. So, right. It's not missing data. Nobody's deleted it. It's just a part of the optical apparatus that does not detect photons.
So, with the redshift, further back in time it is, more redshift.
Exactly.
Sensors have a certain range, optical range, in terms of infrared they can see. So, with the sensors on that array, how far back could they potentially look in time?
Yeah, that is a
Sensors fall off and can no longer see that low frequency infrared.
great question. The short answer is we're nowhere near hitting that limit in terms of just the ability to see those wavelengths. But yeah, maybe hold that thought. So you've mentioned this concept. We don't directly measure how far back in time something was or how how long light has been traveling. What we measure is something called the redshift. And it's kind of a weird idea, but the idea, and a lot of the work, the foundational work behind that was done right here at Lick Observatory, is that space actually is expanding over time. And that means things in space are getting further apart, apparently. And when light travels through space, the wavelength of light gets stretched out. Space expands by a factor of 2, that wavelength gets stretched out by a factor of 2. So that's actually the signal that we see, is that light gets emitted from a galaxy. Maybe it's blue light when it gets emitted. That's pretty short wavelengths. And as that light travels, well, time's going by and the universe is expanding, and that expansion stretches out the wavelengths of the light to redder wavelengths. So we call that the red shift. And that's what we measure directly. And then we have a pretty good model of cosmology that connects directly the expansion of space to the time. So we measure how much space is expanded, and then we have a theory that tells us how long ago that expansion corresponds to. Yeah, so a little bit roundabout. It's really a rate thing. Yeah, it's a little weird to wrap your head around. But anyway, that's the idea of what's going on there. And that is a big part of why the infrared long wavelengths are so powerful, because if you want to look at things further and further back, you're going to have to look at longer wavelengths. And that's basically JWST compared to Hubble, longer wavelengths. So when we look for the most distant galaxies, there's one pretty clear signature. Okay, and this is where it gets a little technical, a little sciencey. So, you know, I'm going to show some more data. Don't worry if you don't follow it. Here's the idea. This is, a rainbow, right? And each color has a different wavelength of light. And our eyes can see these colors. And then we have the ultraviolet, which we can't see at shorter wavelengths. The infrared, which we also can't see at longer wavelengths. And there's a very specific feature that we see in galaxies where at a certain ultraviolet wavelength, all the light from the galaxy just gets absorbed out by actually neutral hydrogen gas. So there's this sharp break. And as light from a galaxy gets stretched out by expansion of space, that break gets moved to longer wavelengths. So what this is showing is just this stretched out to very long wavelengths where that break goes out into the infrared. So when we want to look for very distant galaxies, one of the tricks we look for is to just see this kind of sharp cutoff in the light, where below a certain wavelength, we don't see anything, and then above longer wavelengths, we do. So that's the idea. And here's what that looked like as far as the best effort to find the most distant object as of about 7 years ago. So that little dot there, that I believe is the most distant galaxy that was cataloged by the Hubble Space Telescope. And these are the data. So basically that's the light spread out as a function of wavelength. And you're looking for this cutoff, kind of, okay, so flux versus wavelength. And the idea is that this should look something like this mock-up down here. So what do you think? Looks similar? And then the exact wavelength, or where you see this cutoff, tells you, the redshift, that tells you how far away, how far back in time you're looking. All right, so I want to emphasize this is the best, most distant that Hubble could do. This was a huge effort to do it. You want to see what it looks like with JWST? Okay, so that is pretty clear. Very, very clear, sharp cutoff that you see. And that really nicely pinpoints the redshift, the distance, the time. And so we can tell very clearly with our model of cosmology, we're seeing this galaxy 440 million years after the Big Bang. Pretty far back, even further than that one we saw earlier. Incidentally, okay, so fun thing, this is challenging work. You always have to be careful about uncertainties. So here, there's the break. The break is actually about there, that we can tell very clearly now. So right about up there. Pretty hard to get it right. And that's kind of the nature of the most distant, hardest things to do. But that was the hardest thing to do for Hubble, and now it's honestly pretty easy. You get this, and hey, look at all those other, you see these features here. Oxygen, neon, which we saw before. There's carbon, magnesium, There's nitrogen in there, all those wonderful elements formed by earlier stars. So very exciting. Just the quality of information we get from this is incredible.
Does that assume that the red expansion of the universe is constant?
Is what? No, it does not assume that it's constant. There's a model for the expansion rate, which currently is accelerating because of something called dark energy, right?
It's constant throughout the distance. But isn't it also true that galaxies things affect that acceleration rate?
Yes, and so that's all modeled and accounted for when we get that time of when we're seeing it.
So it's not dark energy or anything like that, which modifies.
Oh, there's dark energy, dark matter, normal matter,
It doesn't matter.
radiation, doesn't matter, yeah, antimatter. It's all folded in there, exactly.
It's all counted.
Yep. All accounted for. Yeah.
Why are the heavy elements so early in the creation of the universe that it can't happen?
Yeah, no, it can, because actually, we'll show you just in a minute. One thing to emphasize, okay, so that was the most distant galaxy that Hubble had found, and didn't quite get the distance or age right, but not by any means the most distant one that Webb has found. Here are just, a few others. These top three are all even more distant than that one. So, and so that's about the farthest back that I know of at the moment that's been claimed or recorded, and that's pushing back to about 325 million years after the Big Bang. And put that in perspective, yeah, that's about 2% of the current age of the universe as we understand it. Yeah, so pretty far back.
But are any of the heavy elements?
Yeah, do we have
Now
some of those?
that top one, I don't think the spectrum is good enough to show the heavy elements. Some of the lower ones there are. Yeah, but let's get into those heavy elements because I mentioned that. Here we go. Here's our periodic table, right? Is this just how you saw it in chemistry class? Yeah, okay. It's color-coded by where those elements are created by their origin. So hydrogen, helium, the blue, that's from the beginning. That's left over from the Big Bang. And pretty well everything else comes from stars, or in some cases, cosmic rays. Different types of stars. So the color coding, this the green stuff, that's here exploding massive stars. Now, those explode pretty quickly. The massive stars don't live too long. They're the live fast, die young, and leave a pretty corpse, right? And that happens on about 10 million year or shorter timescales. Now, other stars, which make other elements, take longer to burn through and produce their heavy elements. Some of these, things like nitrogen and carbon are largely produced on order of hundreds of millions up to billions of years. And a bit of a mix of time scales, so those can take longer. What's really cool, and a trick I like to use, is that by looking at the different mixes of elements, well, you can use that to see how long ago the stars that made those elements had to form. So these ones that make things like neon, oxygen, that happens really fast, cosmic scale, just 10 million years. But things like, strontium, molybdenum, that takes a lot longer. So I was just going to show this quickly. This is some of the stuff that I've actually done with the James Webb Space Telescope. And I go, ooh, what do we have? Let's dig into those data. And here's a nice little galaxy, beautiful, right? Gorgeous structure. Seeing, a few 100 million years after the Big Bang. And when we look at its spectrum, we can see, okay, that is hydrogen there, but this is coming from oxygen, which is telling us that already, which, this happens quickly, you've got these massive stars that have burned up and exploded. And then you look a little deeper, and that is a telltale sign of carbon. Now, some of that carbon comes from these massive stars. A lot of the carbon, at least in our bodies, takes longer to produce. So this is a nice trick for us to look back and see how much carbon do we have? How long ago did those stars have to form? So even if we can't see galaxies way, further than 300 or so million years after the Big Bang, if we can look at their elements, that gives us a clue as to what happened before, which is pretty neat. Yeah.
So our sun, does it have all these different elements in this?
Yes.
It's not just helium, hydrogen, and all these elements?
That's right, that's right. Now it's mostly hydrogen and helium, but it's got little bits of everything else.
And then when it explodes, it creates more of these. But we're really, when we look at those distant galaxies, we're seeing those elements from within stars, not like planets or something like that.
So this is elements, we're seeing the elements in gas, that those elements had to have been formed in a star and then ejected either in an explosion or in this case it's more of a stellar wind. That's a planetary nebula that blasts it out back into the gaseous space around it, what we call the interstellar medium. Yeah.
What element is our sun currently fusing?
Helium. It's fusing hydrogen to helium. It'll keep doing that for about 5 billion years. And then it does more interesting things. Yeah, at least to me. Less so for, not great for life on Earth, but, Anyway, so that's the distant universe, which, I would argue we're really rediscovering. Some of this we're learning from the first time. Some of it's really a renaissance of what we knew before. I just wanted to end with some pretty pictures of things a little closer to home. Things that do look, not like those gorgeous, beautiful red blobs that we were seeing earlier, but, more mundane, run-of-the-mill things like this. So I asked my 5-year-old, what is this? And she said, oh, it's a whirlpool galaxy. Now, this is not the Whirlpool Galaxy. There's one named that. It's a different one. But anyway, so that's an image taken with the Hubble Space Telescope in visible light. This is what our eyes see. And, okay, shall we have a look at it in the infrared with JWST? Yeah. Yeah, really, if you could see in the infrared. But we have a telescope that does that for us. That's real. This is actually real structure. Let's look at it again. You ready? That's so cool. Yeah, you see the star right through there. There's a neat little widget on, if you go to the NASA website, the Webb Telescope.org, there's a little slider where you can, go back and forth between these two images. Yeah, so you can go play with that. It's really neat. Okay, one last shot. This one just dropped. So I just want to emphasize we're about 1 year into operations of the observatory, science operations, and this was sort of an anniversary image. This is in our own Milky Way galaxy, and this is actually the nearest region of our galaxy that is actively forming stars, called the Rho Ophiuchus region. So it's only a few hundred light years from Earth. That's really, really nearby as far as I'm concerned. And what you're seeing here, you've got stars just forming. Some of them even have little shadows of disks around them, and that's where planetary systems form. That's where the planets are being made. That's another really wonderful thing, especially looking at those infrared wavelengths that we get to see. So I'm going to leave it with that one and just emphasize again, this is early days and discovery awaits. So I am very excited to see what we'll learn. All right, thanks a lot.